All right, let's keep a carousing. Now we get to do sight, which is probably, I don't know, the most obvious sense that we all kind of take for granted on a daily basis. And it all starts with a pretty amazing little structure called our eye bezel or eyeball. And we're just going to draw one of those out from kind of a side view. Something like this. And this may be a little long, a little, whoops, not quite there. It's kind of got a bump at the top. Maybe a little too bumpy. Something like that, that'll end there. Just ignore that. Doesn't exist. Okay. Then we got kind of right underneath in here, we got our colored part of our eye. And I have like hazily eyes, so I'm drawing it here in green. This is again like a sagittal cut right through it. And we're looking at the side right through the eye. Okay. Then on either side we got another layer of tissue. Looks something like this. I don't really care that you know the name of this. And we'll label this all at the end. And the back of the eye, we got a special little something something called a retina. Like that. Oops. And this is where the cells that see for us live, is on our retina. And let's see, what am I missing here? A couple other little things. Right here we got a very specialized structure. It's kind of a spherical looking little piece of biological glass. It's a bunch of clear material right there. And it's actually attached to muscles. And if you look at something very close versus something very far, if you're looking at something very close, these muscles got to kind of pull out to pull this lens and stretch it out. And if you're looking at something very kind of far, these muscles can relax. All right, so let's go ahead and label some of this stuff. And I gotta draw one thing on here. So here is the lens of the eye. It's just underneath kind of the colored part of our eye. So just underneath that little colored part, that's where the lens lives. You can't really see it, but when we do our dissection, you're gonna see it. And this thing focuses light on the back of our eye. It's pretty nifty. These are muscles attached to lens to stretch it or relax it. So these, again, if you're doing a lot of close work, they gotta be stretching on it. This is why it'll cause you eye strain if you do a bunch of close work all the time. You know, you're like this, because you gotta be really stretching out that lens, and you can kind of like, I swear to Jesus, you can like kind of feel it, like when you're gonna focus in real close to you all the time. Like you can kind of feel it in there, like just getting pulled all the time. All right, this colored part is the iris, and this controls the amount of light entering the eye. And we'll look at this in lab, shining light into each other's eyes. But you can do this in the bathroom too. Like just go take a flashlight and shine it in your eye when you're looking in the mirror, and you can see it go close up. Your pupil gets smaller. This right here, this hole right here, is the pupil. It's just the hole. Okay. This part here is called your cornea. Cornea. And these cells divide rapidly. These cells divide rapidly and can heal quickly. Quickly. Okay, so the outside clear part of your eye is called the cornea. You can touch it. This will freak some of you out. That's why I'm going to do it. I'm touching my cornea. That your eye liquid, your tears, has a bunch of enzymes in it. Oops. Your eye juice and tears have a bunch of enzymes to kill bacteria. That's why I'm not really too worried about getting an eye infection after just touching my cornea, right? And people who like, you know, putting contacts every day. I don't wear them every day, but I used to. Yeah. Sorry, I was reading something. Your eye juice, tears, yeah. Yeah, if you wear contacts every day, I mean, it doesn't matter even if you just wash your hands, there's still bacteria and stuff on your fingers. And those enzymes in your tears keep you free from infection. Yeah, let's just muscles attached to the lens to stretch. Close work causes the muscles to contract. That's why it's important, like if you're at a monitor all day or even reading a book all day, you want to take like a break every hour or something. Just like go look out a window. You know, something off in the distance. Just relax your freaking eyes a bit. All right, and then the retina. This back here is the retina. And this has a very specialized little area. And this it absorbs photons to allow you to see or like interpret light. This absorbs photons. Did I spell it right? Absorbs? It seems wrong. And right about here, not right in the center of your eye, but just over here, you got a little thick part of it. This is called your fovea. Fovea. And this is your sharp vision. And I usually do this demo. Now, I can't really do it, but I'll do it with you guys in the lab, I think. Yeah, we'll do it with you in the lab. Like you only see, you know, like really sharp vision, like right where you're looking. And the rest, all of the kind of rest of the field of view, it's just kind of blurry bullshit that your brain is, a lot of it is filling in. Okay, and how about this junk in the middle? Well, right here, it's called your optic disc. And then this is your optic nerve. And I'm just going to kind of draw it like that. But it's a big old thick cord. This is your optic nerve. And this goes right to the brain. Okay? Carries the signal to the brain. All right, so what we're going to do, I'm going to just recopy this, but you could just draw a very simplified. Yeah, I'll just redraw it. We'll just draw a little simplified version of this. Okay. All right, so we got our little cornea. And then we got kind of back, the eye goes back like this. Looking a lot better, actually. Okay. And then I've got my little iris. And then we got our lens. Okay. And we've got optic nerve. Got it right here. Then we got the retina. And fovea. Right there. Okay. Beautiful. Okay, and what happens? We've got an electromagnetic wave, also known as light. An electromagnetic wave. That's right. Light is made out of electricity, a wave of electricity and magnetism. An electromagnetic wave, which can also be thought of as a particle. Photons. A photon. Okay? This is a particle or wave of light. If you've never taken physics, you should take it because the world is ridiculous. Okay? And this comes in, and it will hit this lens and it will be bent. Boom. And then it will hit this fovea, let's say. All right? What's funny is that everything that we're actually seeing is upside down on our retina. Like if we were to look at our retina and look at the image of a tree, it would be upside down. But then our brain flips it right side up. It's pretty interesting. Everything we see is actually projected upside down on our retina. Upside down on our retina. Okay. And this is also another really goofy thing, is that the way your retina is laid out is intuitively backwards. All right, so what we're going to do is zoom in on this little part right here. And I'm going to draw this. I'm going to draw this out right over here. So we're going to draw this big. We're going to zoom in. Okay, it's pretty goofy. This is really actually kind of goofy the way this works. Okay. So all the way on the outside of our retina, we got these little things called little ganglions. And they look something like this. Retina is very beautiful tissue, actually. Okay, there's one. And we'll give him a nice little nucleus. And I'm just going to cheat and copy him. Okay, so we got two of these bad boys, like so. We'll come back to these. All right. Then we got these little bipolar cells, just like my sister. They're kind of in between these ganglions and these other cells, okay? Like so. And you know what? I'll take the time. I'll hand draw it. I can do it. Beautiful. You know, I'm getting pretty damn good at drawing with this mouse. Okay, boom. And let's name these. These are ganglion cells. Ganglion. Ganglion, one of my favorite science words. You know what I'm saying? Ganglion, bruh. Bipolar, just like my sister. These are bipolar cells. We also got, of course, these are nerve cells. So we've got our glial cells as well, like our supporting cells. And these guys. Whoops. These guys support these bad boys. Nerve cells are fun to draw. They look so cool. Man, he looks cool. I like him. All right, now we've got kind of the money cells, and we got two different types of photoreceptors, as they're called. These are called photoreceptors. We've got these guys. This one here, this guy right here, called a rod. Okay, it's called a rod, and they got bunch of little membrane stacks here at the end, and they got this big old long part, like so. Okay, and then we got something very similar, but just shaped just a slightly little different way. This is called a cone cell. These are photoreceptors. They detect photons. And he's got the same little membrane stacks that the rod cell does. Okay? And these are photoreceptors. Photoreceptors. Both of them. And this is a rod cell. Rod cell. And this detects low light, no color. Okay, so this detects shapes and they're more light sensitive, whereas this cone cell is for sharp vision and color. Okay. Okay. It's a nice, beautiful little setup. So let's talk about the light coming in. So we got a photon that comes in from the front of our eye, and it's going to hit, let's say, this rod. And let me actually make that in gray, just so it's not the same color as that ganglion. So we got a photon, and it's going to come in. Draw this a little more straight. There we go. Boom. And it's going to hit there, and then signal is going to be sent forward like this. And it goes down the ganglion, and then the ganglion is actually got a big old long axon that then connects to the optic nerve. So these all then become the optic nerve. Okay? So the signal goes to the back of the retina and then gets shot forward down the optic nerve. So this would go to the optic nerve. And goes to the brain. Okay, it's pretty cool. Well, let me just, hopefully this is making sense, but if not, okay, signal to the brain. I'm going to walk through this a couple different ways as well. Show you how this works. Let's go back. So that's the basic setup. Is the photo stuff to absorb the photons is actually in the back of your retina. So the photons got to go through the ganglion, the bipolar, not be absorbed by anything in there, and then it's absorbed by this rod cell, and then the signal shot forward and down to the optic nerve. So if I were to redraw that, so it's like blue-green ganglion over here. I'll move this little thing back a little bit, and we'll just get rid of that. So this is our retina in the back of the eye. So it's like our rod cell was right here, and then our bipolar cell was right here, and then our ganglion cell was right here, and then it connects down here to the optic nerve. Our cone cell was like right there, and then our bipolar cell, and then our ganglion cell. Okay, it's pretty weird. So the photon's got to come in here, boom, hit that stuff in the back, and then the signal shot forward down to the optic nerve. Pretty cool. Okay. All right, let's talk about the eye in a slightly different way now. Now we're going to do a frontal cut, cut off the front of the eye. And we're going to be looking at the back of the eye, the back of the retina. So we're going to be looking at this, but rather than looking at it from a side view, we're going to be looking at it like that. So the rods and cones are going to be deep within this, but we're going to talk about these different structures that we see. All right, so we're going to draw a circle. Draw this pretty big. This is pretty nifty stuff right here that I'm going to talk about right this second. All right, so that's the back of our retina. And right here, this would be our optic disc. So that's where our nerve is plugged into the back of the eye. It's the optic nerve or the optic disc. Okay? So there are no rods or cones here. So we can't see anything there. We'll talk about how crazy that is in a second. No rods or cones here. It's called our, we can't see anything here. It's called our blind spot. And we're going to explore that here in a second. Okay? All right, now all throughout the eye, we've got rods. Okay? We got rods all throughout the eye. So these are rods. Rods. Rod cells. These are photoreceptors. Okay, then our specialized little part of our eye where we can see crisply. We got a dense cluster of cone cells. And it's a very small spot. Like look at the real estate it's taken up. It's not very much. And there's some rods in there too. But not as many. Okay? And this is our fovea, or our sharp, which allows us to have, I'll draw it in pink, sharp color image. All right, and these rods are low light, black and white. Most of your freaking eye is black and white vision, which is kind of nuts to think about. All right, and we're going to look at 3 different areas and see how these kind of, how this plays out. So we're going to look at this cell, like a cell here, right there. That'll be cell 1. And we're just going to draw this out. All right. So if we look at cell 1, it looks something like this. We already kind of drew it. I'm just going to draw it real quick. We got a cone cell. We got our bipolar cell. Oops, didn't change the color. Got our bipolar cell. And then we've got our ganglion cell. But, okay, makes sense. Nice sharp vision. Cone cell. All right, it's no different than the thing that I drew earlier. Okay, now let's move out a little bit and we'll draw, and actually let's not name this cell 1, let's name it area 1. That makes a little more sense. Area 1. Area. Okay. Now let's look at area 2. Let's say we're going to look right here. Okay, area 2. And we'll draw that down here. We're moving a little more to the outside of the eye, a little more to the periphery. Okay, so now let's draw area 2. Area 2. All right. This is going to be all made up of cone cells. Okay. I'm going to draw them quick. Boop. Boop. Boop, boop, boop. And then we've got our bipolar cell. Bloop. Bloop. And then we've got our ganglion. It's a little different though. Here, this is where it gets different. Actually, now let's... So you see how this cell is attached with one ganglion. Like this cone cell has its own ganglion. All right, let's draw out I'm going to copy these to speed things up. For myself, boom, 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 boom. Okay, so these two cells are going to actually share a ganglion cell. Woof. And these two cells are going to share a ganglion cell. Woof. Okay. So these can each absorb a photon, or one can absorb a photon, or the other can absorb a photon. And it'll send a signal down. So these each now act as it's a bigger photon bucket. It's a bigger photon bucket. But we have less resolution, because now it's a bigger pixel. Bigger photon bucket, but less resolution. Okay, and this will become very clear if you're not quite getting it yet. Be very clear when we look at area 3. So let's look at a cell way out here on the edge of your eye. Like we'll look at this one. This is going to be actually multiple cells in here, obviously. Area 3 when we zoom in. Okay. And these bad boys, I'm just going to copy this all again here. Like so. And we'll do it like that. Bam. Boom. Now we got 8 of these bad boys all coming together. And they actually I kind of drew this a little wrong. It's okay though. It's actually kind of the bipolar cells that spread out. I'll fix it down here. It's okay. So these bipolar cells kind of they're the ones that magnify these as well as the ganglions. Boom. Like so. That doesn't matter. I'm not going to test you guys on that. And that boy looking real fat. The idea here is more what I give a crap about. Okay. These guys kind of look like hammerhead sharks or something. I kind of like it. Okay, so we got these vacuum cleaner hammerhead shark bipolar cells, and they connect to now to the same ganglion cell. Right? So where we went from one cell firing on a ganglion to 2 cells firing a ganglion. Now we have 8 cells firing down one ganglion. So this is a huge bucket. So one photon can hit any of these and it'll fire. So we're going to be super light sensitive. Huge photon bucket. Super light sensitive because it's like a big photon collector. Huge bucket for collecting photons. Super light collector, but poor resolution, right? And we'll do a little experiment in lab to kind of test that. Okay, one thing I want to test now, and it might be easier for you to do with the piece of paper, is I want you to take a piece of paper. We're going to look for, oh, I'm sorry, this is area 3. So the farther we go out to the periphery, the more neurons that are on the same ganglion. The more photoreceptors on the same ganglion. And this is what ends up happening. You get better light resolution or light sensitivity, but worse resolution. Okay. Boom, 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 boom. All right, now let's do this. We're going to take a red circle. And we're going to take a black square. And what we're going to look at is this part here, this optic disc. We're going to explore this optic disc. There's no rods or cones here. We can't see anything here. We cannot see anything here because there's no photoreceptors, so we can't see anything there. So what we're going to do is I'm going to cover my right eye, and I'm going to look at the square, and I'm going to move my head closer in, and eventually, right about there, the red dot is disappeared. I can't see it, it is gone. So you're going to close your right eye, and then look at the square. So the red circle should be on the left. You can do it the other way too. Boom, red dot gone. I'm going to close my left eye, look at the red dot, and then the circle will disappear. Or I'm sorry, the square will disappear. Boom, the square is gone. It doesn't exist. And what's interesting, if you do that, we'll do that in lab also, is my brain fills in white. So all day I'm walking around. If you have both your eyes open, the other eye can fill in the information. But your brain is just constantly your brain is filling in bullshit all the time for you when you're seeing. All the time. Like seeing is just electromagnetic waves bouncing around and being absorbed by a photoreceptor. And then your brain interpreting that signal. But we take it as like such truth. But we know that it's not. It's not truth at all. Okay. And you can look up any number of like optical illusions and see how just like messed up our senses are. Okay, one last little thing I want to talk about with the eyes is just how does this work? How do these photoreceptors work? Because it's pretty interesting. How do photoreceptors detect light? Okay. And we're going to draw one of these bad boys in a little more detail. So we got a photoreceptor. I'm going to draw them standing up on end. What's going on here? Draw them nice and thick. Maybe not quite so thick. So this is a nice rod cell. And they actually got kind of a little divot right here. And they look something like that. He's pretty good. Pretty cute. Okay. And they got a nucleus right there. And like I said, all up in here, we've got our, nope, I don't want that. We've got membrane stacks. Lots of membrane stacks. Very similar to like a Golgi or a chloroplast, like the thylakoid membranes in a chloroplast. It's a rod cell. I think I call it a cone cell. I'm an idiot. It's a rod cell. What we're going to do is do a little zoomy zoom. A zoom, a zoom, zoom, and a zoom, 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 and a zoom, zoom. I'm a photoreceptor. All right, way in here. And that would be one membrane. That would be the other membrane. And we're going to talk about what happens. So we zoom way in. One of these membrane stacks looks something like this. Look a little something like this. Kind of looks like a little bone or something. Boom. Perfect. All right. And embedded in this stack, we got a little protein called rhodopsin. Looks a little something like that. This would be called rhodopsin. And within rhodopsin, we got a little molecule called retinal. And I'm sure some of you have heard of this. It looks, I'm going to draw it real quick, a little something like this. And it's got like a kinky tail that goes like that. This is retinal. Retinal. All right. And this boy, let's just talk about it now. This boy, retinal, comes from beta carotene. Beta carotene this comes from carrots. That's what makes them orange. All right, beta carotene. I'm just going to pull up a little picture here of this for you. Boom. So beta carotene looks like this. Oops. Make this a little bigger. You take beta carotene, you cut it in half right there, you can make a retinal. Okay? Or you could convert it and make it vitamin A. All right? Boom, 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 boom. This is cool. So the reason why people say carrots are good for your eyesight is, well, you need this molecule to be able to absorb photons. That's what it's doing. This thing is absorbing photons. All right? It's pretty freaking nifty. And the way it works is when a photon hits this, so we got this rod cell, remember? And light comes in. Light comes in. This is my light. And it hits this. Boom. A photon hits retinal and causes it to bend. Changes shape. That's pretty weird. Causes it to bend. And when it bends, it causes a shape change in rhodopsin. Okay? Some of you may have also realized that this is pretty much the same molecule as retinol, which is vitamin A, which is good for your skin. These are good for your skin. It's pretty crazy. It's all weirdly connected. So if you were to like, I don't know. If you really think about it, it's really weird how all of this stuff is the same. That stuff's really good for your skin. You put it in like serum on your face to reduce wrinkles. I do that crap every night. It's weirdly the same molecule that allows me to see. Very strange. And it lives inside of a taproot of a vegetable, of a plant. That's a dicotyledon. Like what? Doesn't make any sense. Anyway, sorry. So this photon hit this retinal molecule. It then bent because it was hit by this photon. And then it bent rhodopsin. And then rhodopsin, through a bunch of signaling, sends molecules, sends a signal all the way out to this membrane, all the way out to the edge. And I'm not going to draw in the details of all that, but then rhodopsin shape chains, rhodopsin shape change causes a signal to be sent to the outer membrane, not these inner membranes here, outer membrane. Okay, and guess what happens out here? Out here, we got ourselves drawn in blue. What do you think this is? It's the sodium channel. Na. Na plus. A sodium channel opens up. Oops. And allows sodium to rush into the cell. Sodium enters the cell. And what do you think this causes? Causing an action potential. Potential. Boom. Beautiful. And then that sends a signal down to the brain. Boom, 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 boom. I don't have time to get into it, but there's a lot of interesting stuff I could go into there. But that's the basics of what's going on here. So again, let's just go back to this top part here. Works by things bumping into other things. Taste, touch, smell, sight. We're going to do hearing next. Touch, obvious, that's bumping. Taste, that little thing bumps on my tongue. Smell, little thing bumps into my brain. I touch poop with my brain. Sight, a photon bumps into a retinal molecule, causing a protein to bend, causing a channel to open. Just things bumping into things. That's all your senses bumping, you know? All right. I think that's all I want to talk about. Let me just double check here. Yeah, that's it. There's more that I want to do with sight because it's pretty cool, but ear, freaking just as cool. We get to draw a weird snail that lives in your ear. All right, I'll see you in the next one.